All right, hello, Algebra 2, Unit 8, Lesson 1. We're going to start talking about sequences and series. So, a sequence is a function whose domain is a set of consecutive integers. If a domain is not specified, it is understood that the domain starts with 1. So, again, like, for example, if my domain was 1, 2, 3, 4, all the way to n, then there would be corresponding range values such like A1, A2, A3, A4, all the way to A sub n. So again, the domain is like the position, and the range is like the terms of the sequence. So there's a couple differences or different types of sequence. We have a finite sequence, which can be like 2, 4, 6, and 8. Or you can have an infinite sequence, which goes 2, 4, 6, 8, 10, 12, all the way until infinity. Now, you may be asked to develop rules for these sequences. So a rule for this sequence would be something like A sub n equals 2n. I'm going to take whatever n is and multiply it by 2. 2 times 2 is 4. 2 times 4 is 8. 2 times 100 is 200. That's going to give me my answer. You could also, for this one, write it like this. F of n equals 2n. Again, multiple ways to write the same thing. So you may be asked, okay, I want you to find the first terms of some sequences. So if we add the sequence 2n plus 5, or the sequence of f of n equals negative 3 n minus 1. So again, if I were to find my first sequence, a sub 1, I would say, all right, I'm going to plug in a 1 every time I see an n. So 2 times 1 plus 5, that means my first term is a 7. My second term, again, same deal, could find 9, 11, 13, 15, and 17. Over here, again, notice things to point out. I've got a negative on the inside, and then it's raised to the n minus 1 power. So as I plug these numbers in, let's say, all right, so f of 1, if I plug this in, I'm going to get negative 3, 1 minus 1. Remember, anything to the power of 0 is equal to 1. Let's plug in a 2. 2 minus 1 is 1, so negative 3 to the first power is negative 3. If I plug in a 3, and this is what I want you to notice, again, 3 minus 1 gives me 2. Remember, when I have a negative number inside here, this is negative 3 times negative 3, which gives me positive 9. So it's super important that when you have this negative, what ends up happening is your positives and negatives are going to switch. So if you look here, I have positive 1, negative 3, positive 9, negative 27. Because a negative times a negative is a positive, positive times a positive times a negative is a negative. So you're going to keep getting these alternating 81, positive 81, and for the sixth term, if I plug in 6 minus 1, I get negative 243. So again, highlighting the differences of how it's alternating between positive and negative. Dun, dun, dun. Okay. And finally, let me see. What else did I want to add about that? Oh, yeah. So then notice your degree. So if I have a odd degree, it's a negative. If I have an even degree, it's a positive. So again, different types of questions or different types of things I'm going to ask. I'm going to ask you to like create rules, describe patterns. So if we had the sequence, let's say -1, -8, -27, -64, ... I would say, can you write a rule for this? And I say, well, I noticed that 1, 8, 27, 64, those are numbers that are cubed. So if I took 2 cubed, I would get 8. If I took 3 cubed, I would get 27. If I took 4 cubed, I'd get 64. But this is negative. So again, my rule for this would be a sub n equals, I'm going to take whatever n is. N's going to be negative. So -1, -2, -3. And I'm going to cube it. So that's how I would write that rule. Because I noticed that, hey, these are different numbers to the power of 3. We talked about series being finite or infinite. You also have something called summation notation. So for example, if I took the series 2 + 4 + 6 + 8, this would be, and you write it in like a fancy E. So I'm going to get different colors because we got to talk about this. So you're going to put a box here. You're going to put something here. And then you're going to put something here. So the 3 things that you, this is like your starting point. This is how many terms. And then this is your equation. So if I look at this, so again, 2, 4, 6, 8, I see I have 4 terms. So I would, again, filling this out, I would say, okay, you always write, you got to describe kind of what your variable is. So I'm going to say it's I. I'm going to start at the first term. I have 4 terms total, and my equation is 2 times I. So 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6, and 2 times 4 is 8. However, let's say I had a slightly different notation where I add these ellipses, which again means, hey, this is going on forever. So I'm going to start the same. I'm going to have the same equation, but I'm never going to stop. I'm going to go to infinity. So that would be the difference, is that when you notice you have a number going forever, you have to use infinity. Okay, so let's take a look. Let's do 2 examples here. 25 + 50 + 75 + all the way to 250. So since it stops, I know it is going to be a finite series. It appears that I am going up by jumps of 25. So repeated addition is multiplication. So if I'm thinking about solving this, I'm going to say, all right, I'm going to multiply by 25. This time I'm going to use n. So I'm going to say n equals 1. And then I got to think, okay, 25 times what? What is my stopping point? 250. Well, I know that that is 25 times 10. So if I were to write this in summation notation, I would say I'm starting at term 1, I'm going to this 10th term, and my equation is 25n. One other example, let's say it looks something like this. All right, this time I notice my numerator and my denominator are both increasing by 1. So if they're both increasing by 1, I think that means I'm going to have some type of fraction. I'm going to take whatever my variable is. So again, I'm going to call it I. So I'm going to start at I equals 1. And I'm going to say whatever I is, my denominator is going to be 1 bigger. So you kind of make I's curvy. I don't know why, it's just how we do it. So this would work, and then because of these ellipses, I know that I am going to continue on forever. So if I is 1, I have 1 on top, and 1 plus 1 is 2. If I is 2, I have 2 on top, 2 plus 1 is 3. So again, you got to identify what's on your numerators, what's on your denominators, how are things changing. It's kind of like a problem-solving type of idea. And so the last thing that goes into these sums in series or sequences in series is finding the sum of a series. So you might say, all right, I want to, when k equals 4 to the 8th term, I want to find the sum of this series. So that would mean, okay, I'm going to start at 4, so 3 plus 4 squared, and then I'm going to add 3 plus 5 squared, and then I'm going to add 3 plus 6 squared, and then I'm going to add 3 plus 7 squared. So again, notice what's changing. This number right here is changing because that is my variable. So as I solve this, I get, okay, this is 19 plus 28 plus 39 plus 52. Oh, and I forgot one, plus 3 plus 8 squared. Because again, I have to go starting at 4 and finishing at 8 plus 67. And so this sum is going to equal 205. So, that's gross. If I take this sum, k equals 4 to the 8th, I'm going to equal 205. Some kind of special cases. Let's take a look. Let's grab these and throw them in there. All right, here we go. Sums of n terms of 1. Again, if you look at this example, there's no variable in your equation, okay? So again, you're just going to add 1 plus 1 plus 1 plus 1 plus 1 as many times as necessary. Sum of first n positive integers. Again, common example where you are multiplying n, taking the next integer, and then dividing by 2. And then, again, sum of squares of first n positive integers. Again, this is I squared. You're going to end up taking... So it's kind of like shortcuts. It's like instead of having to add up like we did here, 19 plus 28 plus 39 plus 52. If you recognize these equations, these are almost like shortcuts for you to be able to jump in and finish.